This is some tips on how to approach problem number 10 on the Chapter 3 homework. This is Tipler, Chapter 3, problem number 52. In this problem you have a constant acceleration vector given, and it gives you some initial conditions. At time equals 0, the velocity is 0, and it gives you the position vector at time equals 0. Notice it's only in the I direction. So since this is constant acceleration, you actually have two approaches you can take on this. You have to get a velocity as a function of time and your position vector as a function of time. And you can do this one of two ways. You might want to try both ways so you get practice. The first way is to just use our equations of motion for constant acceleration. So for example, we know that v in the x is equal to v0x plus a in the x times t. So you can apply that and then also apply it in the y using your acceleration value and using your initial velocity. Okay, so that'll give you your vx and vy terms. Put that into a vector form. So you have vx in the I and vy in the j. Do the same thing for position vector. There you're going to use your constant acceleration equations in the x and the y. So you have x equals x0 plus v0x t plus 1/2 ax t squared. That'll then give you your x position. You've got your initial position vector gives you your x0, and I would include this over here, a 0j gives you your initial position in the y. So you'll have x and y as a function of time. Put that into Cartesian form. Your other choice that you have to solve these, and this would then be a more general solution, is to just use the idea that you have acceleration as a function of time itself, even though it's constant. So then you can use our general derivative forms that the acceleration is equal to dv dt, and so then to solve for v given a, you have to integrate. So your v is going to be the integral of a dt, and then just do that. You'll have a constant, so you'll have to evaluate the constant, but then you can get your velocity in the x and do another integration using the acceleration in the y direction to get yourself a velocity in the y. And you'll wind up then, they will be the same in this case since it is a constant acceleration. You can do it either way. This way with the derivative forms is going to be more general, and you can use it then to solve all types of problems. And for the other part, for the position, then you'll just use either x or y is equal to the integral of the velocity. So for example, in the x is the integral of v dt. So you have to have the function as the velocity as a function of time. Integrate that. You'll also have a constant of integration there. Use your initial position vector data to solve for that constant. That then gives you a function for position. So then in part B you have to get an equation of y in terms of x. That's what they're asking for, the equation for the path in the xy plane. So you're going to have equations for x and equations of y as a function of time. So you have x is equal to some function in time using your position vector. You'll have some equation in y as a function of time. Okay, so let's call that an f of t. What you have to do is solve one of these for time, substitute it into the other one. I would solve the x equation for time, or time squared, whichever is easier. Substitute that into your y equation, then that way you have an equation of y in terms of x. That'll give you then the path in the xy plane.